everyone. We are Group 6. My name is Vamsi Buntu, and our project is to predict house sales prices in King County of Washington State using multiple machine learning techniques while using the Python coding in Spark platform along with big data technologies. So in the first step, we are going to create a cluster and start a Spark session on the cluster created, and we import all the required libraries which are going further. Next, we import the data file, which is called KC housing data, which is a comma separated file. We set the info schema to true to automatically set the data types of each column from CSV file along with the header is set to true. I'm going to show the Excel sheet of the KC housing data. So this is the data which we are taking. It has the columns, price, bedrooms, bathrooms, and so on. I'm going to show the data dictionary as well. So here is our column names along with the data dictionary and the metadata of the columns. So what we are going to do in order to check them, we use the print schema and check the metadata and see the details as well as using the display command. Here we can see the print schema command which shows the metadata, and then we are going to use the display command to display the data of the CSV file. So in the next step, we are going to drop any null values present in the data in order to prevent any bias when machine learning algorithms and built in the further processing. So we know that the housing prices data is a very common data set available in the internet, but in order to maintain its individuality from any other data sets, we have done some feature engineering. So, and we introduced new columns inculcated from the existing columns, which is better suited for the model creation and evaluations. So the first feature engineering column which we have done is combining the numerical scores of the columns. The columns which we combined are the waterfront, view, condition, and grade. And we are taking the average of all these columns into a new column called house grade, so that we can accurately assess the final grading given to each house in the county in these aspects. So basically what happened here is we have combined the bedrooms, bathrooms, we have combined the columns waterfront, view, condition, and grade, and then we have built a new column. Here we can see this is the house grade. That's the feature engineering which we did. And the second feature engineering which we have done is that we have modified the square foot basement column, which is a numeric column, into a binary values column. So 0 is used if there is no square feet value for basement, and 1 is used if there is any value for square foot basement. So here we can see the basement column is converted into either zeros or ones. That is the second feature engineering which we have performed. And the third feature engineering which we have done is that we merged the years built and years renovated columns into a single column, which is called year, with the latest year data. So the earlier we have two columns, which is the year built as well as the year renovated. So year built and renovated. So we combine these columns into one column, year, which has the latest data. So now I hand over to my teammate Vamshi to discuss further. Vamshi, you're muted.
Sorry. Hi everyone. Coming to feature engineering 4, we have created a column naming house type. This is based on bedrooms and bathrooms. If we see here, we have 4 conditions based on bedrooms and bathrooms. Bedrooms and bedrooms are greater than 5 and bathrooms are greater than 2.5. We have given it as 1, 2, 3, 4, and 1 being very large house, 2 large house, 3 medium house, and 4 small house. After this, we displayed the data in which we can see the house type. For example, for medium house, we have 3. For small house, we have 4. And going on to the next, we have since house type is a string, we have converted house type to integer. and then we have print the schema. If we can see here, house type is now integer. Then we printed the data. Here begins the data processing. Firstly, we have divided the whole data set into train and test with 80 is to 20%. Then we have imported some libraries like linear regression, vector assembler, string indexer, and one hot encoder. Since the feature engineering for which has house type is a multi-class column, we have to encode that column and generate four other for our how many number of classes are there, that many number of columns will be generated. So then we have uh, used vector assembler in which we give all the input columns which are independent columns and these will be uh, created as a array or vector, and the name will be features. Then we have used the pipeline and for the assembler and data encoder. For in the next step, we have fitted the pipe on the train data, and then we have transformed the train data. Coming on to the model, the first model is linear regression model. Basically, any numeric value prediction starts with building linear regression model. So we have started with that, and we took price as the target variable or in a dependent variable, and we have started using the pipeline, and we have built the model, and we fit the model to the train data, and then we fit the model to the test data and transformed it. If we see here, we have predictions like for the price 80,000. It's 80,000. We have predicted minus 67,914, which is not true in this case, but some of the cases were true, and the model performed good enough, but it's not too good to tell that this model can predict the values in a good way. So if we see here for the RMSE value, we have 23,000. Sorry, it's 233,000, which is way more. And if you see the R square value, which is 57%, or like say, if we can say it is more than 50%, and so it can address the data. Coming on to the next model, Prasad will take on from here.
Hi everyone. Hi everyone. This is Prasad. So since we have seen in the above model in the linear regression, the R square and RMS value suggests us that that linear regression which the model which given by the linear regression was not good. I mean, it was good, but it is not the best model. It is not giving us exact results. So that's why we are trying with another model, which is a decision tree regression model. So we have performed the decision tree regression model here. So from this, here also the same thing, like we build a model and then we are checking our results. So you can see here the resulted value and the prediction value. For this also, we have evaluated the model like with the R square and RMS values, but this is also we felt like this is also not the best model which we can get. So that's why we tried another model like a build random forest regression model. So for our data, we are feeling like the best model is the random forest value. Now the conclusion are going to be explained by my friend Rakesh.
Hey everyone, this is Rakesh. From now on, I'll be continuing with the conclusions for this project. For our data set, we have a independent variable as price, which is a numerical category, numerical continuous variable, and we have many dependent variables over there. So we have the price, everything, and we for the dependent variables, we have bedrooms, bathrooms, or square foot living. Everything will be considered over here. For the numerical continuous data, we're gonna use the regression analysis. For the regression analysis, we have covered the linear regression decision tree and the random forest, where we can predict the house prices. Coming to the RMSE, RMSE is nothing but the deviation of the actual and the predicted values. So the lower the RMSE values, the higher the model will be good. So, and we have, along with the RMSE, we have calculated the R square value. R square is nothing but the measure of how the model will be fit to the data. And it represents the more portion you get, like the higher percentage of the R square measure, you'll get the better model. So coming to the results over here, for the RMSC, for the random forest, we got like 1,78,393, which is the lowest of our three models, and the followed by decision tree with the 2,21,000, and the linear regression with the 2,23,000. And coming to the R square value, we have a R square value with the random forest for 75.44%. And followed by we have decision tree with 62% and the linear regression with 57%. So normally there is while compared to both R square and RMSE, we can say that the lower RMSE has the lower RMSE and the higher R square is for the random forest. We can just out of performed all the three models, we can just tell them random forest regression is the best model. And it's not only like depend on this, but if you add more dependent variables on this, you can like the output may be changed, but the output maybe will be dependent. So if you add the correct dependent variables, the R square RMSE going to be more or less. Thank you.